Good afternoon, good evening, good morning. Thank you for joining me. I'm going to talk to you a little bit about advancing carbon verification in an Earth system prediction framework. And I hope you got a chance to see the amazing talks by my colleagues, Dr. Sarah Michala-Fletcher from New Zealand, Dr. Andy Watson from the UK, and Dr. Bob Bruin from the UK. Aren't they amazing? I hope you enjoyed them. I certainly did. So I'm going to talk to you about this incredible increase in atmospheric carbon dioxide due to fossil fuel burning and where it goes. You can see just how far this has come, and it's associated with this spectacular warming in our global atmosphere. And it's not just in our global atmosphere, it's also in our ocean. And you can see here, this is the energy excess associated with that fossil fuel increase. And you can notice that the upper ocean, the deep ocean, are taking up 90 to 93% of that energy imbalance, meaning basically what comes in versus what goes out. Less gets out every year. Even though we are seeing a terrific warming in our atmosphere, the accumulation of energy in our ocean is even more spectacular. So I want to talk about and here we are, the world's oceans were the hottest ever recorded in 2020, even with the pandemic going on. So I want to talk about trust but verify, carbon accounting, and how we do it. And why it's important here in the United States is that the Supreme Court has ruled that it's the law of the land, that the Clean Air Act actually covers carbon dioxide as a pollutant. This ruling was April 2nd, 2007, and the only brief cited was the majority opinion was the scientist brief. And this is specifically the Clean Air Act sweeping definition of air pollutant includes any air pollution agent or combination of such agents which is emitted into or otherwise enters the ambient air, and that without a doubt, physical and chemical substances which are emitted into the ambient air, the statute is unambiguous. Pretty amazing. We also have the amazing Paris Agreement as well. And yet you can see that our fossil fuel CO2 emissions even may have had a significant drop during 2020 due to the pandemic lockdowns. This is from the amazing Global Carbon Project results. You can see this 6.7% decrease projected for 2020. And that's a really big deal. But despite those pandemic shutdowns, carbon dioxide and methane surged in 2020. It's actually continuing to increase in our atmosphere because it's not just fossil fuels. There are other feedbacks going on in the rest of our carbon cycle, in our ocean, in our land, et cetera, and our vegetation. So this is what it looks like. And I know Andy Watson had a similar figure, probably the same figure in his talk, but I just want to point out here that we have a significant uptake of carbon dioxide by our atmosphere. Of course, that's what's hanging out and what Dave Keeling was measuring in our atmosphere, uptake by our ocean, and uptake by our terrestrial biosphere. And we wanted, with this ocean biogeochemical measurements, to reduce the uncertainties in the ocean sink so that we can get a better understanding of the net emissions. That is what comes in and what goes back out. And those goes back out methods could be fossil fuels, could be forest fires, could be organic material respiring back to the atmosphere. Yeah, all kinds of mechanisms put it back in the atmosphere, and some take it up. So reducing the uncertainties in the ocean sink could reduce the uncertainty in the total carbon budget for our planet and for our individual countries. So I'm going to talk about this, the ocean carbon uptake, and I am going to focus a little bit on not just what goes in, but what comes out and what the mechanisms and the feedbacks that are currently playing out in our climate perturbed atmosphere are. They're significant and important. Just remember, even under the lockdown, CO2 still went up. Yep. Okay. So, there's a reason that I'd like to do this. Not only am I interested in what are our fossil fuel emissions, there are many countries that are starting to consider carbon dioxide removal into the ocean, and there are profound worries about what might upwell and come back out. And are we assessing not just as things go in, but what if there's additional mixing next winter? Does it come right back out? And how would we verify these things? So we have multiple interests in this, and it's really tough. This is what it might look like. This is an amazing visualization from NASA, Shira et al. 2020. And what you're seeing is the wind vectors over the air-sea fluxes in the color. And it gives you an idea of the scale and size of the role that the wind mixing has on the emissions, not just on the what goes in and what comes out of our incredible ocean. So I focus on the Southern Ocean. I do other things, but I am a bit of a Southern Ocean junkie. It's true. So what is the role of the Southern Ocean in the global climate system? It accounts for 67 to 98% of the excess heat that's transferred from the atmosphere into the ocean each year. It accounts for up to half of the annual oceanic uptake of anthropogenic carbon dioxide, that's human-derived fossil fuel burning from the atmosphere. And the vertical exchange there is responsible for supplying nutrients that fertilize 3/4 of the biological production in the global ocean north of 30. Just remember, about 3 billion people depend on the protein from the ocean for their basic food and livelihood. So going to sea is hard. I spent almost a year of my life at sea when I was young, and doing measurements, usually carbon, sometimes pH. And you can see just how much of the ocean is still sparse when we look at it in this upper plot, and how much more we can see when we add in to our ships these autonomous profiling floats, Argo. They're amazing. And the Southern Ocean Carbon and Climate Observations and Modeling Project, which is, I am the lead for the modeling. My friend Lynn Talley is the lead for the observations, are ably collaborating with our lead, who is Professor Jorge Sarmiento from Princeton, and our colleagues, Steve Reiser from the University of Washington and Ken Johnson from Monterey Bay. It's been amazing. I am incredibly proud of how many of these amazing floats that they got out and the science that we're doing with them. And I just show you a little bit here of them crawling around in the ocean. Aren't they amazing? And especially under pandemic, I've learned to appreciate the fact that they keep working whether we're there or not. So we are also getting air-sea carbon flux from these floats. And this is amazing paper by Dr. Gray, Allison Gray, who's an assistant professor now at the University of Washington. And they're being assimilated into what Matt Masloff and Ariane Verdi are calling the Biogeochemical Southern Ocean State Estimate, or BSOSI. And I'm going to talk more about BSOSI here in a moment. But basically an ocean solution that is being nudged into as close as possible to what is really happening by the observations available, like our floats. So what we see is these high carbon deep waters reaching towards the surface around Antarctica, spiraling upwards when this is a great Tamsin et al. Nature Communications paper from back in 2017. And we also have an issue because carbon is outgassing in our southern ACC from our BGC floats. Red is outgassing and blue is ingassing. I bet you didn't know that there was that much outgassing, but it's this deep carbon maximum that's reaching to the surface, wind driven. It's extraordinary. And we've actually examined that. This is a paper done by my postdoc, now on to amazing new things, Ben Bronslayer, and a bunch of our epic colleagues through SOCOM and NOAA and the Geophysical Fluid Dynamics Laboratory. And what he showed was that if you add in the fresh water associated with the Antarctic melt and the extra winds that we think are occurring around Antarctica that are not well captured by our climate models, you can actually reproduce the float distribution of pH, oxygen, et cetera, much, much better. And there's a reason that we're worried about that. And it's because there is a huge mishmash in our predictions of how much carbon the ocean is going to take up over the next 80 years. It's a little scary. This is the equivalent of about 100 petagrams of carbon, and it is equal to about a net atmospheric change of about 52 parts per million. It's a huge difference. So the floats are going into the water in one after the other, although it's been very difficult during pandemic, and I have to take my hat off to all the amazing scientists, seagoing as well as in the lab, who have worked so hard to make sure that we could continue to deploy this amazing array. I am incredibly proud of the hard work they put in to make this happen. These biogeochemical floats, and there were 375 in January. I'm sure there are more now, but I'm sorry I didn't download the next plot. The incredible thing is that the National Science Foundation here in the US has funded Ken Johnson and others $53 million to this incredible consortium of top ocean research institutions here in the US to build a global network of biogeochemical floats called the Global Ocean Biogeochemistry Array. And we want to use them because I'm concerned about some climate changes that are occurring. So the Southern Ocean is a critical and precarious carbon cycling engine. Strong winds push surface water north, the deeper water rises to take its place. And if that water hasn't seen our fossil fuel laden atmosphere, and is undersaturated, it takes up carbon. But if that water has rot of ages accumulated in it, if it's older water from deeper, it can rise to the surface and degas. That little degassing that I showed you with the red and the blue, that's what happens. And we're worried that this is becoming a bigger and bigger, that the amount of degassing relative to the amount of ingassing is changing. It could be that we are seeing an increase in the winds that's associated with more upwelling, which is upwelling from deeper, which is causing these things to change. And really, these robot floats are the only way to look at this change in real time. We don't have enough ships to put them all over the Southern Ocean, making measurements like we do with BGC Argo every 10 days, all the way through the winter in the middle of the ice, et cetera, popping up in Polinas. It's extraordinary the work that these floats do, and they're looking at a critical part of our carbon cycle globally. And the reason we're worried is because there's this historical and projected changes in our westerly winds, that the winds are actually drive our big Antarctic circumpolar current and our major circulation, and the pull that deep ocean water to the surface. These are increasing, and you can see that they're predicted to move south and increase in strength. And that has a big influence on how much mixing, how much upwelling, how much the net carbon may go into our ocean. It's a big deal. And it's so remote and so hard to get to and so difficult given the incredible storms, the big waves, that these robot floats are really doing us an incredible service in beaming all that great data back in real time to our to be crunched into our biogeochemical state estimate, et cetera, so that we can do better prediction. So we know a little bit about why, we know a lot about why the winds have moved poleward and increased, and it got kicked off by our ozone hole, but is predicted to continue because of the increase in greenhouse gases that's basically increasing the gradient between in temperature between our lower atmosphere, our troposphere, and our upper atmosphere, which is our stratosphere. So the stratosphere is cooling while our lower atmosphere is warming, and this is driving these winds higher and stronger. We have a lot of different kinds of measurements that say that these winds are stronger. This is the global trend in altimeter wind speed from 1985 to 2018. You can see a few little dots of blue there, but pretty much the winds of the ocean look like they're increasing. If you looked at it from the mean annual wave power, that red line going up, 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 that's the Southern Ocean. The waves are getting bigger. This is a big deal. We're also seeing things like a deep reaching acceleration of global mean ocean circulation over the past 2 decades. Look at those. This is the big global changes in wind speed and wind work. Wow. So, and this is causing our gyres, those big bowls of warm water in the ocean, basically shifting poleward and increasing strength. It's amazing. And J.B. Sally had this amazing paper that just came out this year in GRL, where in the blue, you can actually see the mix layer, the wildly mixed turbulent mix layer, actually mixing deeper down, and particularly in the Southern Ocean. You can see all this blue, but a lot of places all over the world as well, which is consistent with that increase in the winds. So high winds are of outsized importance to the carbon flux. And we did this analysis in GO-BGC in this amazing biogeochemical Southern Ocean state estimate. And you can see the difference between the red line, which is the wind speed actually observed, and the carbon flux observed. It's offset because it's non-linearly related. As you get to higher wind speeds, you get an even bigger increase in the carbon flux. I know, it's amazing. So when we added an extra 20% to the winds over GO-BGC, just what if the winds increased by 20%? The sign of the carbon sink flipped. It went from being a carbon sink where we're taking up carbon in the Southern Ocean, that there's more ingassing, more ingassing versus the outgassing. And then we had, when we increased it by 20%, there was more outgassing than there was ingassing. And this is really, really worrying us. Increasing winds are predicted. And when we run a model with those increased winds, we see greater outgassing that is consistent with the new data we're getting from our biogeochemical floats. So resetting the net uptake of our ocean carbon in right now while we're watching it from these incredible Argo floats. I am really excited. So we went to look and see, are we getting enough wind information to be able to see these big trends? And this is part of the same GRL paper. And basically, we only get between 70 and 80% of the original of the total carbon flux if we only have the wind, the satellites that we currently have up. If we added one more, we'd get 96%. But that means that we may be underestimating our total carbon flux based on our underestimate of the wind speeds by about 20 to 30%. That's a big deal. So we have a project. It's not funded yet. It's under consideration at NASA for an Earth Venture mission called Southern Ocean Storm Zephyr. And we're hoping that if NASA decides to fund us, we'll get that second satellite to bring us up from that 70 to 80% to the 96% of the carbon flux. So we're pretty excited about that. But this is where we think we're headed. We need to make progress towards near real-time carbon accounting that will help us make wise decisions about our global atmosphere and our impact on it. So 15 years ago, we didn't have Supreme Court ruling that the Clean Air Act here in the United States includes carbon as a pollutant. We didn't have an international political agreement to address the carbon cycle. We didn't have carbon observing satellites. We didn't have Earth system model prediction, including carbon and carbon sensitive floats as well. Now we have all these pieces. It is an extraordinary time to be working in this area. So what comes next, I hope, is that we'll continue to build out this carbon observing and prediction system, complete the implementation of the near real-time carbon accounting, publish our top 10 economies' monthly carbon impact, and save the planet, or at least the humans. Thank you for taking the time to speak to me. I appreciate it. Have a great day.